Assalamualaikum. In this video, we will be reviewing the topic of sound through past papers totally. So let's begin. We have this question on our screen, which is part of the past papers. The diagram shows a loudspeaker that is producing a continuous sound wave of frequency 20 hertz in air. So now we are given the frequency as 200 hertz. And we need to tell which diagram shows how the sound causes a molecule at P to move during 1 over 200 seconds. Now you need to know the formula that the frequency is equals to 1 over time, or it can be opposite ways. Time can be equal to one frequency, and this time is given for one complete oscillation of wave. So 1 over 200 is basically in the form 1 over f, and that tells us that a molecule is going to how a molecule is going to move in one complete oscillation. So in one complete oscillation, the molecule goes from completely right to left, because that's how molecules vibrate parallel to the direction of wave motion in a longitudinal wave, which is a sound wave. So we are going to completely cross out option number D, option number C, and we can have some kind of ambiguity between option number A and B, but we know that the time period is given to us is for one complete oscillation, and for one complete oscillation, a molecule moves from its rest position, displaces, and then comes back to its rest position, and that is why we're going to choose option number A. Moving on to the next question that we have, the graph shows at one instant the pressure variation along the sound wave, and the graph that is given to us is a pressure distance graph. And we know that when a longitudinal wave travels, it is traveling in a series of rarefactions and compressions. So rarefactions are the region where the pressure is the lowest, because we have more far apart molecules, and the compression is the region where there is packed molecules, so we have a higher pressure over there. So which point on the diagram represents a rarefaction, and what is the wavelength of the sound? So the line X shows the wavelength. Why? Because it is from one crest to the other crest, so that shows one wavelength. And we need to tell where the rarefaction is taking place. The rarefaction is when the pressure is the lowest. So as the graph suggests, in this point the pressure will be the lowest, and we have Q as where the rarefaction will be. So the rarefaction will be at Q, and the wavelength will be at X. So we are going to take option number C. Moving forward, we have another MCQ. The waveforms are shown on an oscilloscope for a flute and a bassoon playing the same note. The oscilloscope settings are the same for both waveforms. What is the difference between the two sounds? Now, if you observe the two oscilloscope readings, you have the amplitude as the same amplitude, the frequency is the same, and the wavelength also remains the same. However, as you can observe, the quality is different, because one are smooth waves drawn of the bassoon, and the flute doesn't have smoothness in the waves, and that's why we need to take option number C. Moving forward, a boy strikes a rigid metal fence with a stick to create a sound along the fence. A girl listens with her ear against the fence. 1 second after the fence is struck, the girl hears a sound through the air. So, how long will it take for the sound to reach the girl through the fence? Now, in this question, you need to remember that sound travels the fastest in the densest medium. So, the denser medium is solid, and then air is a less dense medium. The sound will travel faster in the fence, because the fence is made up of solids. The fence is a solid. So how long will it take for the sound to reach the girl through the fence? If it takes 1 second for the sound to reach through air, then it should take less than 1 second, because the time decreases as the speed increases, as the speed of the sound is higher in solids than in the air. So we are going to take option number B. We cannot take option number A, because it says 0 second, which is unrealistic and cannot be considered even. So the next question that we have is, what is one of the uses of ultrasound? Now you need to remember the uses of ultrasound, as they have already been explained in our other sound video. Now in this, we are given the options: cleaning jewelry, satellite communication, fluorescent tubes, and optical fibers. Optical fibers, we know that they are used in the light, and fluorescent tubes and satellite communication are both part of the electromagnetic spectrum. So we have started then in the electromagnetic spectrum. So the only option that we're left with, and we already have studied that ultrasound is used for cleaning different ornaments, and that's why we can say that cleaning jewelry is the correct option. Then the next question that we have is, 4 sound waves are displayed on the screen of a cathode ray oscilloscope. Which sound wave is getting louder and has a pitch that is decreasing? So basically, the loudness of the sound depends on the amplitude of the sound, and the pitch depends on the frequency of the sound. This is what we already know. Now, if you observe all the 4 oscilloscope readings, you can identify 2 of the two of the options where the amplitude is increasing. The first option is B and the second is D. Now the second thing that you need to look for is the pitch that is decreasing. That means the frequency that is decreasing. And when frequency decreases, then uh, the graph of the sound kind of stretches horizontally, or you can say that less less sound waves travel per second. So only in part B we can see that the frequency is decreasing, and that's why we are going to circle part B as the correct option. Now let's take a look at some of the theory papers that we have. So the first question shows the cone of a loudspeaker. Sound is being produced. Describe in detail the behavior of the cone and the air which is near to it. So these kind of questions usually come in the chapter of sound, and it can also have a part where they can ask you how the sound wave is after being generated, how is it traveling. So in these questions, what you're going to write is that the molecule of the loudspeaker, they are going to vibrate after getting the energy of the sound wave. Then they're going to displace the air molecules. They start to vibrate, and the air molecules form a series of rarefactions and compressions, and that's how the sound wave is being propagated. So we're going to behavior of the cone and the air near to it. So we have covered 2 points, that the vibration of the cone particles and then the vibration of the air particles that are near the cone as well. The part B states the lowest frequency that a human can hear is 20 hertz. State the highest frequency that a human with normal hearing can hear. Now this is what you need to memorize. It's going to be 20,000 hertz, which is the highest frequency of human audible range. The last part says calculate the longest wavelength of sound that a human can hear. Now, as they're asking the wavelength, and in the part before it, we have been given the frequency as well, then we know that we need to use the formula V is equals to F lambda, which is frequency multiplied by the wavelength. We are given the sound speed at 340, and we need to find out the wavelength. Now we are given two frequencies. The first is 20 hertz, that's in the question, and the second that we have written is 20,000 hertz. And they are asking the longest wavelength. Now the longest wavelength will be when the frequency will be the lowest, because they have an inverse relationship. As you can see that frequency and the wavelength are being multiplied over here. So they have an inverse relationship, and that's why we're going to take the smallest frequency, which we have as 20 hertz, into the wavelength. So the wavelength will result in 17 meters, and you need to take care of the unit because wavelength is a length, so we are writing meters. The next question shows one swimmer in a race starting before the signal. Now the swimmer is called back by a loud, low-pitched sound from a loudspeaker positioned just at water level. There are loudspeakers that have been positioned, and you've been told in the diagram as well. Now the speed of the sound is given as 330 meters per second. The first part states that describe how the loudspeaker causes the sound to travel through the air. This is the same as the first part of the previous question that we have discussed. The second part states explain in terms of wave properties what is meant by loud and low pitched. This is similar to the MCQ that we did. The loud means having a higher amplitude, and low pitched means that lower frequency. So there will be less sound waves produced per minute. Less sound waves produced per second. The third part states the swimmer is 0.57 meters from the loudspeaker. When he hears the sound, calculate the time taken for the sound to reach him through the air. Now in this, we are given the distance and we have the speed at 330 meters per second. So we're going to use the formula speed is equals to distance upon time. The speed is 330. The distance that we have is 0.57. And from this formula, we can get the time as 0.0017 seconds. Take care of the unit as it is seconds over here. Now we need to explain how the time taken differs when sound will travel the same distance through air and through water. Now, as I have already discussed that the sound travels faster in a denser medium, so water is more denser. That's why the sound will travel faster in water, and less time will be taken for the sound to travel in water as compared to air. Moving on to the next question that we have, it shows how ultrasound is used to produce an image of the heart. You need to observe the diagram clearly. There is heart labeled, and there is ultrasound transmitter and detector. And ultrasound is traveling from the surface of the skin to the heart. We need to define ultrasound. Ultrasound can be defined as any sound wave that has a frequency higher than the audible human audibility range, which is or more than 20,000 hertz. The second part states the ultrasound has a wavelength of 1.2 into 10 to the power negative 3 meters. The speed of this ultrasound in the human body is 1500 meter per second. We need to calculate the frequency of the ultrasound. Now, we have been given the wavelength and the speed, so we know that we're going to use the formula V is equals to F lambda. And by this formula, we're going to substitute the values. The speed given is 1500. Then the frequency given to us is not given, and the wavelength is 1.2 into 10 to the power negative multiplied by frequency. So from this we can find the frequency as, so you can find the frequency this way. The last part states ultrasound is a longitudinal wave. Describe how the particles in the body move as the ultrasound passes. Now in this, the first point will be that the particles in the body are moving as they are vibrating to and fro from their rest position. Then the second point will be that these vibrating particles form a series of compression and rarefactions, and thus the ultrasound wave is propagating through the through the particles in the body. Now the last part of this question states there are small bubbles of gas in the body. Why these bubbles are expanding and contracting? Now, if you focus on the terms expand and contract, you should know that expansion of the particles will mean that there is a low pressure region, and contraction of the particles will mean that there is a high pressure region. So, as you know that in a longitudinal wave or a sound wave, there is always rarefaction and compression, which are the low pressure and the high pressure regions. That's why, because of these formation of rarefactions and compressions, the particles are either expanding and contracting, and that thus the pressure difference is created, which is why this process happens. Moving on, a sound from an electronic organ is played into a microphone which is connected to a cathode ray oscilloscope. Figure 6.1 shows the trace on the cathode ray oscilloscope produced by the sound. Now, in this graph of the sound wave, you can see that the amplitude is decreasing and the frequency is also decreasing. So the horizontal line, which is marked as the trace where there is no sound, how the figure 6.1 shows that the loudness is decreasing, and the loudness is decreasing. The loudness is decreasing because the amplitude is decreasing, as I've already mentioned. However, I made a mistake. The frequency is not decreasing because the pitch remains constant. As in the second part, they say that the pitch of the sound is constant. So at first glance, what I had in mind was the frequency is decreasing. However, it isn't, and the pitch of the sound is constant, and that was going to be because the time period or time taken for one complete oscillation remains constant, as it is given to us at 0.020 seconds. And that's how the frequency remains constant, and pitch is related to frequency. What is meant by the frequency of the wave? Frequency of the wave is the number of complete oscillations in 1 second of a wave. The time for one complete cycle of the wave is 0.020 seconds. We need to calculate the frequency of the wave. Now, we are going to use the formula frequency is equals to 1 over time. We have been given the time as 1 over 0.02, and we get the frequency as 50 hertz. So this frequency means that 50 complete oscillations can take place in 1 second of this sound wave. Then the last question that we have is describe a method for measuring the speed of sound in air. In your account, state clearly how the sound is made, what measurements are taken, how the result is calculated, and what precaution to produce an accurate result. The answer to this question can be this direct method of measuring the speed of sound. In this direct method, there is one person which is having a pistol, and the second person which is standing away from the first person by a known distance as given as 150 meters is having a stopwatch. So basically in this experiment, the first thing that we need to tell is how the sound is made. So the sound is made from the pistol. What measurements are taken? The first measurement that is taken is the distance between the two people that are standing away from each other. Then the second measurement is of time. How do we calculate time in this experiment? The first thing that we do is the person who is holding a pistol is going to fire the pistol. Now, when he is going to fire, the other person is going to see the fire first and then hear the fire. So when he's going to see the fire, he's going to start the stopwatch, and when he's going to hear the sound of the fire, then he's going to stop the stopwatch, and that's going to be the measurement that's going to be taken. How the result is calculated: in order to get the speed of sound in air, we divide the distance by time, and that's how the result is calculated. One precaution to produce an accurate result can be that we need to take multiple readings because human reaction time in oh, starting and stopping the stopwatch is present. That's why we need to take multiple readings. Then we can increase and decrease the distance of the two people that are standing so that we can have multiple readings for the distance as well. And we can also cancel out the effect of the wind or the influence of the wind in this experiment by switching the places of these two people, and we are going to take the average of the results. So those are the precautions that we can take to produce an accurate result. With this, we are done with the review of sound through past papers. Thank you.